So this is the sort of first session of the London Probability Seminar, which will be running similar kind of thematic one-day workshops throughout the year, maybe 4 or 5. And so we should just get on with the business, I think. We're very pleased to have Hermann Thorisson here from the University of Iceland. And the topic, as you know, today is coupling. And now we're going to be, well, Hermann will give 2 introductory lectures on coupling of stochastic processes. Thank you very much.
Thank you very much. It's nice to be here at Imperial Probability. Grand name of the page, web page. Yes, this is some sort of an introductory talk, but since I am more a theory man than an example man, it's going to be very much theory, but I try to let it look like examples. So the title is Coupling Stochastic Processes, but I will actually start with random variables and talk a lot about just random variables for the first hour. And then the second hour will be devoted to a general theory of coupling stochastic processes in a particular way. So what is coupling? Coupling is, as Tom Liggett wrote in the beginning of some paper, it's any joint construction of random variables or random processes or random things. It's a very general thing, so I will present this from my point of view, from my little corner in the world. I was introduced to coupling through the classical coupling of Markov chains in the late 70s, and for several years, I thought of coupling as that coupling. And then I realized that people were doing all sorts of other couplings. And that opened up tremendous fields, really. And I cannot tell you everything about coupling. I will tell you how coupling looks from my point of view, or my standpoint. So here is the definition in terms of distributions. So if we have some collection of probability measures indexed by some set I, defined on some measurable spaces, different spaces possibly, a coupling of this collection is a single probability measure defined on the product space of these spaces, and such that Ps is the marginal of P on this space for all S. So it is creating some sort of dependence between probability measures. Any dependence. This is the distributional definition of coupling that I sometimes use, but I like the other one, which is on the next slide, better, random element definition. And I will be using that in this talk. A coupling of a collection of random elements is a family of random elements defined on a common probability space such that this guy here has the same distribution as the corresponding guy up there. So how are these definitions related? Well, PS on the other slide are the distributions of these x's, and P is the distribution of this collected thing here, and I write it in parentheses to stress that they are defined on the same probability space, while these guys need not be, can be defined on different spaces. So just why I use this, it's because I'm used to work with a huge probability space where I can have everything I need whenever, take a uniform random variable or whatever, not having to go through stepwise constructions, extensions in each step. So we take just a big space. So the underlying probability space need not be the canonical one, but any probability space. So I keep it open what the space is. Now, so the random elements here, they can be real-valued random variables, they can be stochastic processes, or any random things taking values in arbitrary measurable spaces. I am now going to go to this case here, random variables on the line. The first example is the Poisson approximation. So I'm starting at the level of an elementary introductory book on probability. This is in all such books. And what does this say? So let these i's here be 0, 1 variables or Bernoulli variables with parameter p, probability of having 1. So you can see this as repeated trials. You have a trial, you repeat it n times independently, and you register whether you have a success or not. So you write 1 when you have a success. And if you sum the i's, you get the total number of successes, and this is a binomial random variable, NP, with some particular probability mass function. But this structure of it is really the essence for me of the Bernoulli, of the binomial variable, that it is a sum of IID 0, 1s. Okay, and why is the Poisson lambda, namely a random variable with this probability mass function? Okay, so this result here is usually obtained by use of Stirling's formula. I think that's just generic, that it's done that way. So if we take p here, this lambda divided by n, then this probability tends to the Poisson probability. That's the standard thing we teach our students in the first year. Engineering students, and I think any people who take probability at the university level. Now, Stirling's formula is usually not proved. But this result here, it's an immediate consequence of the following inequality, which we can easily establish by coupling. So I will do that on the board there. So what does this inequality say? Well, I'm using total variation norm. You don't need to introduce it in the elementary classes. You can just take the absolute value if you like. But it works for the total variation norm. And the total variation norm of the difference of the distribution of these two guys, I write this means the probability distribution of xn. So if you put in a set A for the dot, then you have the probability of xn being in A. So this is the difference of two probability measures. And the total variation is supremum of all of the differences over all measurable sets A. In this case, all A of integer sets A. So there is no measure theory really here. I put the 2 here in front. Many probabilists don't like that. I have it there because I want, for if you are looking at the differences of general measures, of bounded measures, the total mass need not be 0, and the definition of total variation would imply, in general setting for signed measures, would imply that there should be a 2 there, and I stick to that. it's a nuisance, but it's there all the time. It's just a matter of definition. So it is really the supremum norm times 2. Okay, so let's do this. So I will start with n equal to 1 and then take n greater than 1. Okay, so now enters the uniform. So let u be a uniform random variable on 0, 1. It's going to be there throughout these 2 hours. So now u is somewhere on the line 0, 1. And if we put the mark 1 minus p here, the length of this interval is 1 minus p, and the length of this one is p. So now we define a random variable I to be 0 if u ends up here, and to be 1 if u ends up here. So it is clear that I is Bernoulli. I should have used that. I is a 0, 1 variable with parameter p. Now, for the Poisson variable, so the Poisson probability, if we have the parameter lambda equal to p, that would be the case when n is 1 here, is when k is 0, the probability is what? It is e to the power minus p, and when k is 1, it is p times e to the power minus p, and so on. We don't use the other probabilities. And now I have to do it this way. I'm sorry, you will know it immediately what I'm doing, but I don't remember so many things. Okay, so here is the exponential. And here is the line 1 plus x. So, okay, good. This holds for all x. So take x equal to minus p. And you have e minus p greater than or equal to 1 minus p here. So, this probability is greater than or equal to 1 minus p. So this number is somewhere here. Maybe I put it here, e minus p. Okay, and then this number, if we add it to this one, so add here, we are here somewhere. Okay, now to the construction of the coupling. So if u ends in this interval up to here, we put n equal to 0. N is going to be the Poisson guy. N is going to be this guy. And if u is here, then we put n equal to 1, and so on. So you see the probability of of ending here is correct. It's e to the power minus p. And the probability of ending here is this, and so on. So we get this probabilities for this n. Now, look at the probability that I is equal to n. There are two cases where this happened. It's here and it's here. So this probability is exactly 1 minus p plus this length, which is p e minus p. And to make this a little bit cleaner or simpler, rather look at this thing here and recall that we had this. So this is greater than or equal to this. So we will have that this probability is greater than or equal to 1 minus p plus p 1 minus p, which is what? 1, these p's cancel, so it will be 1 minus p squared. Okay, so the probability that the binomial and 1p is identical to the Poisson p is no more than this, and the probability that they are different, that they differ, is less than or equal to p squared. So if p is 10%, this will be 1%. Okay, so we have established this. No, we have not established this. So now comes a slide. So what I created at 10 o'clock last evening. I'm not sure everything is okay here, but so I'm introducing a concept, a very simple-minded concept, a coupling event. So this was the total variation. You have two random variables. This is the total variation. And the event C is a coupling event if the two guys, if the coupling is such of, this is a coupling of the other two guys. If these two guys are identical on the coupling event. So in particular, we could take C equal to this. So that's what many people would consider to be the coupling event. But it's convenient to see in the continuation to have C sub event. Oh, here is a theorem. Why is that not gray? Okay. It's okay. Need not be. So if C is a coupling event, then the total variation is no more than twice the complement, probability of the complement. In particular, if we take C equal to this, the complement of this is this, so we would have this. And this is the proof. So it's just simple-minded things that are here. We take this difference. We split this probability in two parts. Outside the coupling event and inside it, same to the y. And now I forgot, and I will just put it here. I forgot to put hats on these guys. Anyway, so this thing is this. That's correct. Okay, so next step is to put hats on them. That's a very typical coupling argument. So you start with the things you're interested in, then you do the coupling, and work with the coupling rather than these guys. So here you can put the coupling. There is no y here, so it doesn't matter whether you have x or x hat. They have the same distribution. So put hats on these guys in your mind. You see what I did? On this event here, the two guys are identical, so I can place x hat there. The hats are very important here. So, okay, this cancels. Very good. Oops. Now, this is negative, so if we drop it, we get an inequality. I will drop it. And this thing here is less than or equal to this. So this difference is less than or equal to that, and by symmetry, the other difference will also be less than or equal to that. So you take the absolute value here, you take the supremum, it's less than that, and you multiply by 2, and you get this. Okay. So we are here. And we had an inequality there that I was going to use. I'm sorry. Where? This one, yes. Okay, I'm going to use this particular form of it when C is the coincidence, when C is equal to this. So, yes. This is less than or equal to p squared, so the difference is less than or equal to p squared. So let us now go back. Yes, that's what we wanted. N is 1, so we have this. So it's established for n equal to 1. Now let's establish this for general n. That is easy. So what we do is we take n IID uniforms. Create this coupling for each of them, end up with this. And now these are the i's in the definition here. So xn is just the sum of these i's. So just like here. Now I would like to see y as a sum of the n's, and that's on the next slide. If you have IID Poisson P, the sum will be Poisson NP. Okay, so we have created a coupling. I'm not having hats on that coupling. Sometimes I have the hats, sometimes I don't. Sometimes it's not. The hats can be important to distinguish between the original guys and the coupling, but sometimes it's not. So we have the i's, xn is this sum. We have the n's, y is this sum. Okay, so now what is the probability that this x, I should have hats on it. I won't. What's the probability that these two sums of i's and n's are not identical? Well, this is less than the probability of the union right? If they don't agree, some coordinates must disagree also. And now we can take the sum. And this is, we know, less than p squared. So this probability is less than or equal to n times p squared. So we have this. Why do we have this? It's because of this inequality here. So this is less than or equal to p squared. So put in p squared there, and you get this. Okay, so this was coupling. This was a Poisson approximation. We have approximated Bernoulli by Poisson, and note that it is the p and the n that are the original sort of the data we have. And y is constructed. So this is an approximation for the distribution of this by the distribution of the Poisson. While here it is really p is changing, and it's lambda that is fixed. Anyway, so how do we get this from this? That's easy, as you probably have noticed here. This is equal to that in the case when lambda is np, in this case. And then, you see, it goes to 0. And this is elementary. Well, someone might say, you need the existence of the uniform. Yes, for this construction there. But we can do this differently. We can do this by just constructing the joint distribution of I and n without the uniform. Just write out what it is. So we don't need any measure theory for this. It is completely high school mathematics and as rigorous. Okay, this was the Poisson approximation. I'm not doing Poisson approximation, so I could give the whole lecture on Poisson approximation if I was someone else. But Poisson approximation is used a lot, and this is just the very, very elementary introductory example. Note in this construction that we could have different p's when we constructed the i's. So then the sum would be the sum of different IID Bernoullis. And we still would have something here, this. And this would be pi here. So we have, and this would be the sum of the pi squared. And this is sort of just to indicate that this is not limited to this particular problem. And coupling goes hand in hand with Stein method. To do Poisson approximation, and sometimes coupling is good, efficient, sometimes Stein method is good, efficient. I think most of the time it's the Stein method that wins, but coupling is usually simple, and but it can be very, this is very crude. It's only in the case when n is equal to 1 that we have an identity here actually. In this construction, we can't do any better than this. But when we start summing IIDs, we lose. It's in this part here. This step is bad. This one is bigger than that one, and then here is another bad step. Okay. I might mention that there is a result saying that I will do it here, that this inequality, there is another inequality saying this. No n. This gets bad when n is large. This is the same all the time, whatever n is. But this one gets good when p is small. So it is a balance you have to take there. But if you have this one, you see that you can always efficiently or quite well approximate the Bernoulli, the binomial by the Poisson. N doesn't matter. So it is wrong what is stated in the elementary textbooks that you need a large n. That's only because of this that you need large n. The important thing is that p is small. The event has small probability. then it really doesn't matter how large your n is. Because of this. But that's not part of this, because this gets worse with n. Yes, okay, that was the Poisson approximation. I have spent some time on it, but I have also done this. It's a preparation for the stochastic processes thing later, that I will dwell on this slightly. Coupling event means that the coupling guys are identical, and this is a key inequality, and in this, when the two are the same, this is the standard form of it, really. And here was the proof. And here is another theorem that I'm not proving. There exists a maximal coupling. There should be an exist here in front. Did this also, yes, late last night. You can actually turn this identity, this inequality, into an identity. So you can maximal couple. You can make them coincide so that this is equal to this. This is fixed. You have different couplings, and then this is different, varies. And then there is a coupling, actually several couplings, where you can achieve identity, called maximal coupling. Yes. Okay, now to next example. I'll look at this as an example. It's a stochastic domination. I will clean this board. Okay. Stochastic domination means the following. So we have, well, I am moving the pens over here. I had a blue one. Okay. Okay. So let x have a distribution function f, and y have distribution function g. So this is the distribution function of x, and this is the distribution function of y. G is f, this is g. Stochastic domination means the following. If you draw a picture, we have f here, and below it we have g. So g puts mass higher up on the axis than f. That is stochastic domination. Now there is a theorem saying that if you have stochastic domination, there is a coupling so that you have actual domination. So this guy is never less than that one. Here is a way to create it. So take U, uniform as always. So U is here. This is the interval from 0 to 1. You go out here. You go down here. You call this x hat. I think you've all seen this, but I will do it in detail. So this guy, x hat, has distribution function f. And why is that? It's because if you take x here, so that this is less than or equal to x, then you would end up here. So this holds if and only if u is less than or equal to fx and u is uniform, so the probability of that is fx. So the probability of this event when there is a hat on x is fx. So this guy has distribution function f. Okay. Now do the same to y. And this is sort of obvious. So here is the coupling. Okay. I remember I had a comment on maximal coupling. So I will stop here, take 1 minute for maximal coupling. So sorry. Maximal coupling was this last line here. So the standard simulation type of way to do maximal coupling is the following. If X has density F and Y has density G, you have F here. Note that if we would choose a point uniformly at random under the curve F below the X, above the X-axis, and take the X coordinate, the probability that this coordinate would be less than an X is just this area here. So this guy has the density F. Okay, so now take G here. And create a coupling in the following way. Choose a uniform under F. If the uniform ends here, go down here, call it X hat, and also Y hat. So they are identical if this happens. If the point U ends there, you go down here to get your X hat, and you move over here and choose a uniform guy on this area above this curve under this one. Go down here and get your Y hat. And this is maximal coupling because the probability of this here is the integral of the minimum of F and G, which is twice, the total variation norm is twice that. No, 1 minus twice that, yes. So this is the identity. So they don't agree with this probability, and multiplying by 2, you get the total variation norm. And so you will get an identity here. This can be done for more variables. You take an age here, like that, and then this would be not a good age. It should be above the other one also. Anyway, you see the idea. You can do this for many variables, and it's done in simulation. It's a simulation trick. Okay, so back to next slide. Back to next slide. Yes, we've done this. Now this. It's strange. This should be light blue anyway. So this is not part of the theorem. This should be anyway. So this belongs to this theorem. So convergence in distribution. It's this thing here that the probability, the distribution of xn tends to the distribution of x whenever this x has probability 0. This is weak convergence on the line. And theorem says if we have weak convergence, then there is a coupling, so we have actual pointwise convergence. Usually this is written as almost sure convergence, but since I have a sort of generic probability space, I allow myself to throw out a null set. Not to have to write almost surely. Okay, so well known, and how to prove this? This is easy to prove. No, not really. It's not as easy as this one. Okay, so let xn have distribution function fn and x have distribution function f. And do the same trick. Here is f And for convenience, I will draw it like this. F1 is here, F2 is here. So I'm letting the F's increase towards the limit, but they could be doing it in a completely different way. Okay, so you choose your U here, go out to F, go down, get X hat, go all the way to F1, get X hat 1, X hat 2, X hat 3, and so this is to suggest that it will go to the limit. And that's some manipulation to prove that. Okay, so this is really could be in second course, so probability without much measure theory and general mathematics. Okay, so here is a third theorem. Let the xn's be continuous, so they have densities Fn. Here is a theorem. If there are densities so that the limit is a density of the random variable x, then there is a coupling so that the xn's actually hit the limit at some random index n, finite random index n. And let me illustrate this here. So, okay, so here we have convergence in distribution, and this is what happens in that case. So this is n-axis, and this is the real line, and here is the limit. And then the other variables, this is 1, 2, they wiggle around and get closer and closer. That is this. This is x hat 1 and so on. So this is to illustrate this limit result. But this limit result says, I will denote it in this talk today by this, with a small d rather than d for density. It looks like this. So here is the limit, x hat, and the guys come in, maybe hit the limit, and then at some random time n, random index n, it just hits the limit finally and then just stays there. I will put this within quotation marks. Okay, so 3 implications. If you see an implication and have a theoretical mindset, you ask, can you turn it around? What did happen now? Did something happen? Oh, yes, yeah, I changed this yesterday evening. Okay. Okay, so this is where we started. I was just illustrating this limit here. Okay, but what is the difference here? Well, this is convergence in the discrete metric, where points are close if and only if they are identical. So this heavy thing here can be turned into, what did I do now? I'm on the wrong computer. Sorry. It can be turned to this if we use the discrete metric. Here we have the standard metric on the real line. Here is the discrete metric. So this is exactly the same result except different metrics. Okay. Now I can move on to the equivalences. Yes, this can be turned around, quite obvious. if this is less than or equal to some little x, then this would also be less than or equal to that. So we have this property. So it's obvious. And the next one is also well known. Why is that? Well, you can go from this to this, because if you take a bounded function, f, continuous function, here and there, then you will still have the convergence if f is continuous. And then by bounded convergence, the expectations will converge, and that is one of the characterizations of weak convergence. So we have this. But what about this? Can we turn this around? I wouldn't be asking if you could. No. So, we just have this. But, in the proof of this result, we didn't use that this is a density. We only used, well, you didn't see the proof, that the lim-inf is a density. And that's actually a much nicer condition, because lim-inf always exists. And if we have this condition, the weaker condition there, then equivalence. Convergence in discrete metric is equivalent to lim-inf being a density. And now I will introduce a symbol for this, which you already have seen in this talk. It's not accepted. So let this denote here that xn tends to x in density. I call this convergence in density, namely that this is a density of x. That's convergence in density. Because, yeah, then I can place this, because this condition then is written this way. Because of this equivalence, I think it should have a name, this condition, and convergence in density is fine for me. We can discuss that afterwards. Okay, so now you see these two are quite similar. Convergence in distribution, convergence in density, same result with different metrics. Okay, so next question is, are we stuck on the line? Are those things only true on the line? Well, this thing here is hard to extend in this way to higher dimensions. We could do it if this was a vector, but that's not a very good concept. Stochastic domination is not defined this way in higher dimensions. Same here, we can't define convergence in distribution this way, so we have to change that. So let me move on. So how far can this be generalized? Well, this theorem can actually extend all the way to partially ordered Polish spaces, proved by Strassen in '65. Stochastic domination means that if you take an increasing function, the expectation g of x should be less than or equal to the expectation g of y. That's the definition, very simple definition, and this is true. It's a very complex proof. I'm looking for someone to give me a simplified version of it. There have been attempts to do that anyway. So it's someone I know claims that people never check the proof because it's too difficult. I don't know. I haven't. Okay, so move down here. Okay, this is the standard definition of weak convergence of probability measures. in metric spaces. So this denotes this. And the result from the line goes all the way to separable metric spaces. Skorohod proved in 56 that separable complete spaces are okay, Polish spaces. And Dudley in 68 extended it to the separable case. So this result is quite general. But what about this one? We have continuous random variables. So are we stuck on the line, or can we go someplace with it? Yes, we can. Okay, so now we define this thing here. And now I actually remove this quotation mark because I now have defined what I mean by convergence in distribution, in density, sorry. I didn't have it properly defined when I drew this. Okay, so now define it. It's a completely general space. There's no restriction on the space. You can have the discrete metric on a general space. So let this denote that xn tends to x in density, which means this. And what does this mean? So Pn, so xn has distribution Pn, x has distribution P, and we can write each Pn as, what should I write, as lambda and a nu, where this lambda is the absolutely continuous part with respect to P, and this is the singular part with respect to P. And then dPn dP is so this is a sub-probability density. And the lim-inf is 1 almost everywhere P, means this. This means that. So that this sub-probability densities increase to 1, which is the density of P with respect to P. And then this is true. And the proof is exactly the same, basically, as for the line. It's, in this case, much harder proof, and in this case, even much harder proof. But here, the same. Okay, so I think I will hit you with the final slides before the break. This talk is sort of splits into what you have seen and then a talk on stochastic processes, which is a continuation of this. But there is an intermediate phase where we actually step into stochastic processes, but not in the way I will do after the break. So I will now go to stochastic processes. So what I'm going to do, I'm going to focus on this result. And I'm going to apply this result to stochastic processes considered in finite time windows. So I will let the windows grow, and I will explain this in a minute or two. So I will focus on this theorem. This theorem can be extended in a particular way to stochastic processes. And it turns out that this theorem then is a corollary. And this is not an easy theorem. Okay. What did I do now? Yes, I just took away the red stuff. This is what we have done now. Okay, so now look at this thing here. The density theorem. It's just what we had. This discrete metric result can be extended to stochastic processes considered in a widening time window. And here is that theorem. So zeta is an unconventional stochastic process. I call it random sequence in this talk to have a name for it. You see, it's discrete time. It could be done in continuous time in D space, but I'm not messing with that here because I want to focus to be on another thing, but it can be extended to continuous time. So you have a sequence of random elements, and first you note that there is a final element there. So I'm including infinity as part of the time axis. Actually, in the application to the distributional convergence theorem, the separable space theorem, this is going to be the x, the limit, while the guys here are sort of leading up to x. So just so you know, I need this final element there for the application that I'm heading towards. Also, I'm not assuming that they have the same state space. So it's inhomogeneous state space processes. It really is not a big thing because you could always take the products, the union of the spaces, and but it's cleaner here to say that they have different spaces. Okay, and then I put a k on the zeta to truncate it. So we have just a vector of k elements here, finite window. Call it finite time window. Okay, so now comes the theorem. Discrete metric convergence in widening time window. So now we take a sequence of things like that, plus a limit candidate. And then this claim here, which is a convergence in density claim, is equivalent to this kind of claim, which I will explain in a minute. But so in all finite time windows, assume that the processes converge in density. Not the full length of the process, but all finite segments. This is not the limit here, but this is the limit here. For all k, all finite k. This is equivalent to that there exists a sequence of integers k, which are going to be increasing time windows, and a coupling of these guys. You see that I'm only looking at the guys up to time k1, k2 in no widening time window, and do the same with the coupling here. So this guy has the same distribution as that one, this same distribution as that one, and so on. So there exists a coupling so that there is a random variable n such that when little n is greater than or equal to this random index, then all the widening windows coincide. So you have a sequence of processes, and you let the sequence grow. N is growing this way, and the process grows that way. And so when you're up in the nth process, you are looking at a particular window of the process, and then when you go higher, you have a bigger window, and so on. So in the end, you will hit the window of the limit. This is not very hard to prove. It's maybe concentrated 1.5 page. Using just basic measure theory and radon-nicotine theorem in a simple way. Okay, so this is the theorem, and it has an extension. I guess I had the extension. No, it's here. It has an extension. Moreover, if the end element of this guy, that is, if all the end elements have a state space which is general, no restriction on the finite thing, and the finite windows, so this guy is the end of this one. These are the other variables. So if the other variables are n-valued, so the important thing is that they are countably valued. So cleaner to call it n. Then we can extend this coupling, which is sort of a truncated coupling. It's only of the finite windows. We can make it a coupling of the whole thing. So here we go up to K1 and then can fill in the rest to get, well, here. You go up to K1 and then you can fill in the remaining variables, and in particular the limit variable, or not the limit variable, the end variable, at the end of time, and have it here. So this is what I wanted here, but you need a condition, and I took a simple condition to do this, because this can now be used to prove this theorem. And I will do that to you. Here's the proof. So you probably need to have seen this done before, but let me explain what the trick is. Why do we need a separable space? It's because you can in a separable space, you can split it up into nested partitions. So here is a space, call it E. Let it be a separable metric space. Split it up in sets of diameter less than 1. Then split each of those into sets of diameter 1/2. And then each of those into space of diameter 1/4. So after doing this k times, you will get a partition of the space with ik ups. Ik is an element of n to the power k, so we've done it k steps. So this partition would consist, in, when k is 3, would consist of these parts, and so you have a nested sequence, and you can define these guys the following way. So when xn is in this set here, you let the setup process indicate that. So the zetas are telling you at level k in what set you are in the k-step partition. So as k increases, you get closer and closer to the limit. Skorohod assumed that he had a complete space to be able to use completeness to get the limit. Dudley used another trick, which is sort of embedded in this whole theory here. But from this, we have that these probabilities tend to this. Because P continuity set says that the boundary has P distribution. P is the distribution of x And the p continuity set means that this is a p continuity set. So convergence in distribution means that the probability of this tends to the probability of this. And so the probability of this tends to the probability of this. And if you divide by this here, you see that the density with respect to this distribution tends to 1. So we have this, and then you can use the stochastic processes theorem to get this, that there is a random n, so that from n onward, the x hat n's, x hat n is going to be this end variable here, and this is going to be this one. So the x hat n's are in the same sets as the limit. And so this thing here applies as follows. When n is large, x n hat is in the same set as x hat. So for large enough n, this is less than this, which goes to 0. Bingo. So I stole 10 minutes of the stochastic processes part, but it was a little bit stochastic processes. So now I think it's appropriate to take a break.